Today, I'm going to show the synthesis of dibenzyl or dibenzylideneacetone by Adol condensation, starting with about 290 milligrams of acetone and 1.06 grams of benzaldehyde in a vial. Then I mixed the solution thoroughly so the two reagents were fully combined. In a separate beaker, I added a stir bar, then 10 milliliters of 10% sodium hydroxide in water, followed by 1 milliliter of ethanol. The sodium hydroxide provides the basic conditions needed for the Adol condensation, and the ethanol helps the organic reagents mix more evenly in solution. At this point, the mechanism begins with the base removing an alpha hydrogen from acetone to form an enolate. That enolate then attacks the carbonyl carbon of benzaldehyde, forming a beta hydroxyketone intermediate after protonation. Under the same basic conditions, that intermediate loses water to give the first conjugated eno, benzalacetone. Because benzalacetone still has an alpha hydrogen, it can undergo a second condensation with another benzaldehyde molecule to form dibenzalacetone. Next, I added the benzaldehyde acetone mixture to the sodium hydroxide ethanol solution with stirring. Once the base comes in contact, the mixture begins changing color as the condensation started, which is a good sign that the product is forming. The reaction was then allowed to stir until the solid product began to appear and the mixture became more opaque and yellow. After the reaction was complete, I isolated the crude by filtration and washed it with cold water to remove residual base and soluble impurities. At this point, the crude material already showed the expected yellow color associated with conjugated products like dibenzalacetone. The next step was recrystallization. I dissolved the crude solid in a minimum amount of hot ethyl acetate, then allowed the solution to cool slowly so crystals could form more cleanly. After the solution reached room temperature, I placed it in an ice bath to maximize crystallization, then collected the purified solid via filtration and let it dry thoroughly. Recrystallization is important here because it removes impurities and gives a cleaner product for analysis. After purification, I analyzed the product by proton NMR and COSY on a benchtop instrument. In the proton NMR spectrum, dibenzyl shows aromatic and vanillic signals. Since this was collected on a benchtop instrument, the resolution is lower than on a high-field spectrometer, so there was some overlap between one of the vinyl signals and the aromatic region. Even so, the pattern is still consistent with the expected structure. The COSY spectrum was also useful because it helps confirm which protons are coupled to each other, even when peaks overlap in the proton. COSY can help connect the vanillic and aromatic spin systems and support the assignment of the product. Overall, dibenzyl is a useful compound in organic synthesis because it is a straightforward example of an Adol condensation product and a good target for learning purification and spectral analysis. Thank you for watching.